This is Yang Liu from City University of Hong Kong. Today, I will share our recent work for human hand tracking. This work is cooperated with Chengdong Lin and Professor Zhenjiang Li. Human hand tracking is estimating positions of different skeletal joints on human hand in 3D space over time. With such capability, many useful applications can be benefited. There are several existing works. One kind of works are based on cameras, like leap motion. However, they are not portable. They have limited surface area, and their performance is influenced by the ambient condition. One work further utilizes wearable thermal cameras, but its performance is still affected by the ambient condition, like temperature. To this end, some works utilize glove or isolated EMG sensors on user's arm, but they are not user-friendly and convenient. So in our work, we want to enable a lightweight and portable hand tracking system. We utilize a commercial armband to track user's hand, and this system can be deployed on user's mobile phone. First of all, I give a demo video of our system. To track a human hand, the widely used sensor called EMG sensor. It can sense the activation level of our muscle. Existing biomedical models require multiple EMG sensors deployed on specific spots to sense strong and isolated signals from each piece of muscle. However, sensors on one armband can only sense one cross-section of our arm. We may only have weak and mixed signals from multiple muscles. So we cannot directly use the Bayer models with such armband data because their main recursive functions will be ineffective. However, the Bayer model provides 4 suggested steps to track human hand with physical meaning. So in our work, we utilize a RN to enhance the Bayer model because the RN can extract the complicated time dependency from the input signals. From this model, we can estimate the positions of 14 skeleton joints, and this model assumes the wrist cannot move. Then we upgrade hand poses with arm orientation. With this upgrade, we can see in this figure, the hand poses with the same hand shape, but under different orientations can be distinguished. We introduce the gyroscope data in our model. Now we have 2 types of signals, and we want to fuse them together. Because they have different importance under different hand gestures, so we propose a design to let the model automatically focus on the more important inputs to improve the performance. In addition, we consider 2 practical issues. First, we provide a plug-and-play version for new users to directly use our model without training. Then we consider the armband position, because the position to wear armband cannot be exactly seen each time. The first one is the distance difference between the armband and the wrist. This difference mainly changes the signal strengths, so we can utilize normalization to handle it. The second difference is a rotation difference. We have a baseline setting that a specific sensor block is pointing to the direction of the index finger. However, whenever users wear the armband, they don't need to remember the number in our work. They can let any one sensor block point to this direction and conduct one-time warm-up gesture. With these 3 steps, our system can automatically virtually reorder the EMG signals to match the baseline setting. We evaluate our work using 2 armbands with 18 subjects. In particular, we train models from the data only from 1 armband and 10 subjects. and test the performance of both armbands with all 18 subjects. The average error of our system is 2.6 centimeter, and it achieves an obvious error reduction compared with the bear model. Now I conclude my presentation. Based on the topic of human hand tracking using a commercial armband, we have 3 design considerations. First, we enable the hand tracking of 14 scaling points with arm orientation. And then we provide a plug and play version for new users, and we also consider the armband wearing position each time. That's all for my presentation. Thank you for your listening, and I'd like to answer any question from you.